Hello, everyone. This is Engineer Mary Rosaliti Alandeska, and welcome to our class Food Chemistry Lecture. I already posted on Canvas on how our course will be running for this semester. So, as what I have said, let me reiterate to you that all our TDOA will come in the form of lecture recordings. So every week I will be posting lecture recording for the topic that we have for that module. Aside from that, we are going to have our consultation hour every Friday, and that would be from 10 a.m. to 11 a.m. So before Friday, I would like you to read and start working on your module for that week so that if you have any concerns, if you have questions, you may raise all of that during Fridays. So you start working on your module before Friday of each week. By Friday, we are going to meet for our consultation hour, which is from 10 a.m. to 11 a.m. And our TDOA, our TOA, will be this lecture recording. So our schedule for TOA will be we will not meet during our schedule for TOA because we already have this recording. And if you have concern, you can also inbox me on Canvas. Okay? So let me give to you our lecture for this week, which is all about matter. Since we are talking about chemistry, and we always start with our discussion of chemistry with matter. Okay, so allow me to share with you guys my screen and all the slides that I am using here are taken from different sources, and you may refer to such sources in the description box below. I will enumerate all the sources as I give credit to the authors of these slides. Okay, so what is matter? We already know ever since from grade school to junior high school to senior high school, matter is everything that occupies space and has mass, okay? So it's what the world is made of. Now, from your grade school, we learned that matter is classified into solids, liquids, and gases, okay? Or those are the three states of matter. And when we reach junior high school, there is another state of matter, which is plasma. So it became four states of matter. Now, what are these? Okay, so we have the solid. An example for that is the ice. We have the liquid. An example of that is water. And for the gas, an example of that is the water vapor. And for plasma, that is now very hot. It is the ionized gas. Okay, and we will be talking more about plasma later. So, as we all know, solids have definite shape and volume. Of course, it has mass and occupies space. The particles of solid are packed tightly together. They are very close to each other and they only rotate and vibrate in place. However, the particles of liquids take the shape of their container already. It has definite volume and of course, it will also take the volume of its container. It has space, occupies mass, and the particles of liquids are loosely packed. Okay? They have medium energy levels and the particles will flow around each other. Next, for gases, gases spread out to fill the entire space given and do not have definite volume. Gases, of course, has mass, and gases, of course, take up space. Now, the particles in gases move freely. They go around in random motion. Okay? They have lots of energy because the particles in gases tend to escape from its container. Now let us proceed to plasma. An example for plasma is lightning. We also have other examples later. Plasma is a lot like a gas, but the particles are electrically charged. So that's what I meant earlier, the particles of plasma, or it is also known as the ionized gas. Okay? So since they are electrically charged, they have extremely high energy levels. So the energy levels from solid to plasma increases. Now we have our examples for plasma: lightning, the sun, nebula, the neon lights, and the auroras. Now, how do matter change from one phase to another? Okay, how will it change from solid to liquid? Okay, so it requires energy in order for us to change the state of matter. So if we want to change the solid to gas, solid to liquid, we have to add energy. And if we are going to change from solid to gas, we also have to add energy. Okay, so say for example, we have solid ice. We want it to turn into liquid water. So you must put energy there. And that energy is in the form of thermal energy. So you're going to heat the ice in order for it to turn into water. And we call that change of phase as melting. Now, if we are going to turn liquid to gas, say for example, liquid water to water vapor, you have to add energy again. You have to boil the water in order to turn it into steam. Okay. Now, boiling, that you need energy in the form of thermal energy, and the change phase for that is called as evaporation. Now, we can also turn solid directly into gases without passing the liquid state. An example for that, if we have an albatross air freshener, it is solid, the circular one that you put in the washroom. Okay. Now, in time, that albatross will be gone. Okay. So it will not turn into liquid, it will go directly into gas. Okay. So we call that change phase as sublimation. Okay. Now, gases can turn back into liquid, and we call that condensation. And liquid can turn back into solid, we call that solidification. And in the case of the plasma here, the gases should be ionized, more energy to be added in order to change that into plasma. Okay? So when energy is added, the particles move faster. And when energy is taken away, the particles move slower. So the ice will melt because of thermal energy, ice cream melts because of thermal energy, and so on and so forth. Okay. So that was our discussion earlier. Solids can turn into liquid, liquid into gas. It needs energy, and we call that state change, phase change, or physical change, because we are only changing the physical um look, or the physical characteristic of matter. Now, aside from those four states of matter, we also have the fifth state of matter. We are already in college, so I hope that you also had this already in your senior high school. We have the Bose-Einstein condensate. Sorry. Okay, this was proposed by Satyendra Bose and of course Albert Einstein. Okay, so according to them, okay, they define the Bose-Einstein condensate, or Beck, to have separate atoms or subatomic particles that are cooled to near absolute zero temperature. So when we say near absolute zero, the absolute zero temperature is 0 Kelvin. So when we say 0 Kelvin, that is equal to negative 273 degrees Celsius. Now, on Earth, here normally we cannot have negative 273 degrees Celsius, but we can only have that condition specifically if we are going to have it artificially. Okay, so we can reach that condition. We can have negative 273 degrees Celsius artificially. So these subatomic particles that are cooled at the absolute zero temperature coalesce into a single quantum mechanical entity, one that can be described by a wave function on a near macroscopic scale. Okay, so that is the Bose-Einstein Condensate. And examples for that are the superfluids and the superconductors. Again, Bose-Einstein Condensate, they do not, we cannot see that naturally, okay? But they are artificially or synthetically made in the laboratory under the condition of the absolute zero temperature. All right. So if that is being said, it is at an absolute zero temperature. So that means that it is here having the lowest energy among all the states of matter. Okay, because as the energy increases, okay, the energy is in the form of thermal energy. So that means plasma has the highest energy and Bose-Einstein condensate has the lowest energy. Okay, so these are our examples again for the five states of matter. Going here to Bose-Einstein condensate, the temperature becomes lesser, and going to plasma, the temperature becomes higher. All right. So let us proceed to the classification of matter. Matter is classified into two main um, classification. Okay, so if matter can be physically separated, we call that as a mixture. But if matter cannot be physically separated, we call that as a pure substance. Mixture is further classified into two. If the composition is uniform, we call that as a homogeneous mixture or a solution. And if the composition is not uniform, we call that as a heterogeneous mixture. Now, for pure substances, if it can be chemically decomposed, we call that as a compound. But if it cannot be chemically decomposed, that is already an element. And heterogeneous is further classified into two, the colloids and the suspensions. When we say colloids, these are mixtures having those very, very tiny particles, as well as for suspensions, they are both heterogeneous, having very tiny particles. But for suspensions, the particles are larger than the colloids. Okay? So we have our what we call this Venn diagram for the elements, compounds, and mixtures. What are their differences and what are their similarities? You have that on your module. Now, for this one, okay, so let's have our example. Graphite is an element. Okay, why is graphite an element? Because it is made up of pure carbon. Okay, carbon is an element. Pepper. Pepper is a heterogeneous mixture because it is not composed of only one substance only. Sucrose or sugar. It is a compound. A sugar is made up of three atoms or elements, which are carbon, hydrogen, and oxygen. So it is a compound. The paint is a heterogeneous mixture because it is not uniform in its composition. While the soda is a solution, it is uniform because soda is uniform in its composition. Okay, so further discussing them one by one, an element is composed of identical atoms. So examples are the copper wire and the aluminum foil. The copper wire is only made up of copper and aluminum foil is only made up of aluminum. While for compounds are composed of two or more elements, just like the sugar earlier. Okay, so we have this our table salt. Our table salt is composed of sodium and chloride ions. It is sodium chloride. So that is a compound. For pure substances, there are two laws that are being observed, the law of definite composition and the law of multiple proportions. So that means the number of sodium atom will just be 1:1 with the number of chlorine atoms rather. And for the sugar or sucrose, it is C12H22O11. So it must be definite. Okay, the carbon must have that definite number, the hydrogen must have that definite number, as well as the oxygen. Okay, another example for a compound is we have carbon monoxide and carbon dioxide. They are two different compounds, although they are made up of the same elements. So for carbon dioxide, it is made up of carbon and oxygen. Carbon dioxide is also made up of carbon and oxygen, but oxygen in monoxide is only one, and oxygen in dioxide are two already. Okay, so with that, it must be consistent. Okay, observing the law of definite composition and law of multiple proportions. Now for mixtures, this this can be a combination of two or more pure substances. So we have again heterogeneous and homogeneous. Okay, now for mixtures, we have solutions. It is homogeneous, made up of very small particles that are soluble in the solvent. Okay, and it does not undergo Tyndall effect. So when we say Tyndall effect, that is the absorption, or that is the ability of light to pass through it. Okay, so for solutions, light can pass through it because the composition is uniform. Okay, so the particles do not settle, they dissolve. So an example, of course, is the rubbing alcohol. Rubbing alcohol is made up of alcohol and of course distilled water. Okay, so say for example 70% ethyl alcohol. 70% of that is the ethyl alcohol, and the rest is distilled water. Okay, so if you can see, it is only one composition, right? It is uniform. All right. Now, aside from solution, which is homogeneous, we also have colloid, which is heterogeneous. They are made up of medium-sized particles, and it has already Tyndall effect. Okay, the particles don't settle. Say for example, milk. Milk is an example of a colloid. Okay, and there are types of colloids: aerosol, foam, emulsion, salt, solid foam, solid emulsion, and solid salt. Okay, so you have your examples for that and what they are made of, if gas plus liquid or solid, and so on. And we also have suspensions. Suspensions are heterogeneous. They are already made up of large particles that settle, okay? And they inhibit Tyndall effect. So an example for that is the freshly squeezed lemonade. Okay, so other examples, we have the mayonnaise that is a colloid, muddy water suspension, fog is a colloid, salt water is a solution because the salt dissolves completely in water. Italian salad dressing is a suspension because they have large particles in it. Okay, so that is all about the classification of matters. So, what are you going to familiarize with? If the properties are not uniform, that is a heterogeneous mixture. If the properties have fixed composition, that is a solution, and if it is uniform. If it is chemically decomposable, it is a compound, but if it is not chemically decomposable, that is an element. All right. So here we have hydrogen atoms, that is an element. We have hydrogen attached to oxygen, that is a compound. Okay, H2O. There is two hydrogen atoms in each oxygen atom. So that is water, a compound. Okay, now this is a mixture. You have hydrogen and oxygen, they do not react with each other. That is already a mixture. As well as for D, hydrogen and oxygen, they do not react with each other. That is also a mixture. Okay, but for hydrogen and atoms that react with each other, indefinite composition, two hydrogen in only one oxygen, that is a compound. Okay, and we will proceed to our last slide. Again, if you are watching this, the credits of the slides are in the description box below. So kindly take a look at that for your reference. Now, let us proceed to the properties of matter. Okay, what are the physical properties of matter? Okay, so of course, we already talked about the state of matter, solid, liquid, gas, plasma, and of course, the Bose-Einstein Condensate. Okay, so for solids, they have elasticity. So when we say elasticity, that is the property of matter that can be stretched, or ability of matter that can be stretched. Strength, the ability of solids to not break after a large force is being applied to it. Stiffness, the ability of solids to resist change in shape upon the application of a force. We also have malleability, the ability for metals to be hammered into thin sheets. Okay? Ductility, the ability of metals to be drawn into fine wires. So that's why we have copper wires. Brittleness, the ability of solids to easily break. And we also have for liquids, we have the property which is diffusion. Okay, the ability of liquids to spread through another material. Surface tension, the ability of liquids to behave like an elastic skin. So, say for example, the drop of water. Okay, the water will not spread right away. Okay, but it will form something like a mountain. Okay, because that is surface tension. It is elastic, okay, in the surface. Adhesion, molecular attraction between different substances, that's why they adhere. And the opposite for that is cohesion, the molecular attraction between the same kind of substances. Okay, so water molecules attract each other because of cohesion. Capillarity, the climbing action of water. Okay, so when you sip a soft drink with straw, that is capillarity. Now let's move to gases. Gases also has diffusion, ability of gases to spread through other gases. Compressibility, all gases can reduce volume. Okay, now let's have the physical properties in three states of matter. Okay, solubility, when a substance dissolves. Okay, not only solids dissolve, gases also dissolve in other gases. Liquids also dissolve in other liquids. Thermal conductivity, of course. Everything has thermal conductivity. Okay, insulators, even insulators, it also has thermal conductivity. But the conductors have the greatest thermal conductivity. Density, the mass per unit volume, of course, pressure, the force per unit area. We are just going to have a run through with this. And let us now proceed to the physical quantities of matter, the mass, weight. And what is the difference between mass and weight? Mass is the amount of substance in the body, while weight is the gravitational pull towards the Earth's center. Okay, so this is in contrast to what we have as our clinical weight. So when we go to the clinic, it is weight that is listed there. If we are going to answer or fill up forms, it is weight that is being asked from us. All right, but scientifically, mass and weight are different, okay? Because weight, again, is the pull of gravity towards the Earth's core. Okay, that is the gravitational force. Okay, so say for example, we are here on Earth, our mass, let's go to mass. Our mass is 48 kilograms. Now, when we go to the moon, we are still 48 kilograms because we do not gain any weight. Okay, We do not gain any mass, okay, and it's just the same, okay, when we go to the moon. However, our weight changes because in the moon, the acceleration due to gravity is one-sixth that of the Earth. Okay, so we can compute that in physics. We can compute weight to be mass times acceleration due to gravity, and we will have the same weight. That's why in the moon we seem to be weightless. We float there. All right, but we have the same mass. Okay, so we have volume, amount of space, density, done already, specific gravity, as well as pressure. Let us proceed to the chemical properties of matter: reactivity, flammability, toxicity, stability, acidity, conductivity, tarnishing, fermenting, and oxidation. Okay, so there are two changes: physical and chemical changes. Okay, so for this one, a metal is rusting. Of course, that is chemical change. A coal is burning. The coal, rather, you burn the coal, that is chemical change. The food spoils, that is chemical change. And if you are just going to crush the food, that is only physical change because there is no change in composition. Okay? Chemical change is the change in composition and new products are formed. But for physical change, it's only the change in size, change in color, texture, and so on. And there is no new product that will form. Okay? So this one, you just cut your hair. That is physical change. You just slice a tomato. That is also a physical change. However, if you leave a tomato there and the tomato rots, that is no chemical change. Okay? Now you shred paper. Okay? Shredding paper, that is only physical change because you are only turning the paper. Okay? But if you are going to burn the paper, you have new product which is ash, that is chemical change. Cracking of concrete, physical change. Now let us proceed to intensive and extensive properties. Okay? Intensive properties do not depend on the size of the system or quantity of matter present in it, but they are dependent on the nature of substance present. Okay, so say for example, the pressure, temperature, density, surface tension, boiling point, as well as solubility. They are intensive properties of matter. While for extensive properties, they depend now on the quantity of matter present. That's why extend, okay, outward, okay. See for example, mass, volume, number of moles, internal energy, enthalpy, and entropy. Because the mass increase, volume can increase, volume can decrease. Those are extensive properties of matter. Okay, so that is just all about matter, and everything is in your module. I will stop sharing my screen. Okay, so kindly read your module and kindly start working on your module before Friday of each week for our consultation hour. So again, this is our TDOA. We will not be meeting on the class schedule that we're supposed to have. Okay, so you have more flexibility on how to learn from our course. Okay, you have the module, you have this recording, you can watch this recording anytime. But I wish for all of you to read, start working on, and watch this recording before Friday of each week for our consultation hour. And during our consultation hour, I will be addressing all your questions and all your concerns. And if you have immediate concerns, immediate questions, you can directly email me on Canvas. And do not state your name anymore, just give me your section code. Okay, because that's what I'm looking at, your section code and the course that you're having with me. So thank you very much for watching and subscribe to this channel. Goodbye and see you during consultation hour.